left off polyatomic ions, how to organize them by the charges and to write them out in your own hand and maybe color coordinated like I showed here to help you remember what they are and how to find them. So they're also on the periodic table. So we're going to refer back to those, or to your own handwritten list is ideal. You could also use the periodic table that I've provided. And then we started talking about making neutral compounds. Neutral ionic compounds have equal numbers of positive charges and negative charges so that they result in zero overall charge. If the charges are the same, such as in sodium chloride or sodium cyanide, then it's just 1-to-1. We just put them together to form a compound. So go ahead and do that for these. I will also name them. We talked about the cations get the metal names, and the anions end with IDE. So that would be sodium chloride. KCl, it's a 1 plus and a 1 minus, so there's just one of each of them, and that is potassium chloride. So go ahead and fill those out. It works the same way with polyatomic ions. So we'll just name the two ions potassium nitrate. Remember, the 8 means it's negative with oxygen. Magnesium oxide. Magnesium sulfate. Go ahead and say it as you're writing, because when you say it out loud, it helps you remember. I know it seems like such a baby thing to do, but that's because that's how learning works. So aluminum is a +3, nitrogen is a -3, so one of each. Aluminum nitride. And with the polyatomic, aluminum phosphate. All of those have zero charge overall. They're neutral. So when we go to the chemical room, the chemical storage room, bring out a bottle, it doesn't shock us. It's neutral. There's no electricity coming from it or going into it. They're neutral, zero charge. We need to use that to guide how we write compounds. Now, there's a couple ways to look at this, and we're going to introduce the crossover method, where we're going to bring the charge of one down and the charge of the other down. So here we'll put these together, and we'll need 2 chlorides and 1 barium. So when we write our compound, it's going to be BaCl2. Now the charges are gone because it's neutral, it's charge balanced. This is the smallest neutral subunit of an alternating lattice array of opposite charges. So we can always check that algebraically. We need to have this total charge be 0, right? So it's a neutral compound. I'm going to introduce C bar just for compound. So neutral compound. So we have 0 equals the charge on the barium is 2 plus, and we've got 2 chlorines, and each one brings a 1 minus, and so that equals 0. So we know that it's neutral. Let's use the crossover method for aluminum and oxygen. So we're going to think about bringing just the numbers down to form Al2O3. Now let's check that that's neutral. We've got 2 aluminum, and each brings in 3 plus, and we've got 3 oxygen, and each one brings in a 2 minus, and that equals 0. So we're done. That is a neutral compound. K3P, potassium phosphide. Okay, we're going to use that with the polyatomic ions as well, crossover method. But now we have all of those atoms functioning as a unit, so we will put them in parentheses. So this is a 1 minus on nitrate, so we'll bring that down, and we'll bring the 2 down, but now we need to show NO3 parentheses 2. Those nitrates act as a unit. So put it in parentheses because there's 2 of each thing. All right, is it neutral? We want to check. Strontium brings in a 2 plus. We've got 2 nitrates, and it's 1 minus each, and that is 0, so we know it's neutral. Oh, I made a mistake. We have to bring that 3 down. So the balance that we're looking for here is the charge balance. We want to make sure that our charges total up to 0. So what I did was I put in parentheses NO3 minus, and I'm going to have 2 of them. So that 2 is going to distribute. So separately, if we want to write an equation, we could say, okay, 1 strontium plus 2 nitrates are going to form this compound, and then it's balanced. So if we're balanced equation, we have 2 sides on the arrow, but when we're just forming the compound, we're looking for overall charge equals 0. And I can show superscript, right, and show the 0. It's not necessary. If we write a compound, then we know that it is neutral. It has to be neutral. We'll do it one more time with zinc and phosphate using the crossover method. We will need parentheses around that phosphate, and there are 2 of them. So let's see, 3 zinc, they bring in a 2 plus each, 2 phosphate with a 3 minus each. That is plus 6 minus 6 equals 0. So we've formed a neutral compound. The 4 in this case is a subscript. And what we multiplied up here was the 3, that was the charge. So they're different, they're doing different things for us. If we look at our ions, let's look with the polyatomic ions, we are saying these work together like one thing. It just comes together in a unit. Right, we could talk about drawing, let's draw a phosphate. 5 electrons for phosphorus, 4 times, how many valence electrons in oxygen? 6 plus 3 is 32 valence electron in this ion. We have to use our brackets and show the charge outside.
It looks like that 3 minus should distribute both to the O4 and to the phosphate, but it's not. It's like that whole PO4, just think of it as being like 1, doesn't distribute and then become like, 12 minus or whatever for the oxygen.
No, they don't separate, but they're shared.
I think when we try to balance those elements, probably we need to just focus on only the ions instead of each element in the phosphate.
Just the charges, yeah. We're not balancing equations yet. We're just trying to make neutral products. Up, we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Everything has a full octet, and if we want to account the charge, we would use a formal charge, and that produces a -1 on each oxygen and a +1 on phosphorus. So I'm not asking you to know how to do that, but I'm showing you that the charge is distributed inside that unit. So when we write PO4 3-, we're saying these stay together and it all shares that charge. When we form a compound, it has to be neutral. So right now, we're just trying to find the formula unit for the smallest neutral subunit of ionic compounds. So because like here, the zinc, there's 3 zinc and they bring in a total of +6, that completely balances with just 2 phosphate because the phosphate brings in 3-. So they counterbalance each other and our formula unit has 3 zinc and 2 phosphate. So the 4 oxygens are there. There's 8 oxygens in the formula unit. Now we're not yet balancing equations. There's no arrow. We're just trying to make the product. Okay, now we did talk about making the smallest neutral subunit. So if you have a crossover method with something where there are multiples of each, you would think from the crossover method that you have PB2O4, but that's not the smallest ratio. We have to reduce it to PbO2. So you could think about how many of these how many oxides do you need to counterbalance the 4? If we look at this compound, we have for lead, sorry, that's a 4 plus, 2 minus for oxygen, then we have 4 minus 4 equals 0. So this is good enough. That is neutral. So again, we want the smallest neutral formula unit. And it works with polyatomic ions too. We'll just keep them together. So we have tin is bringing in 4 plus, and we have 2 sulfate with 2 minus each, and that is 4 minus 4, and that is 0. So this compound is neutral the way we wrote it. This is a huge skill. We're going to be doing this all quarter long for the rest of the quarter. We have to go backwards and forwards, naming and formulas and naming. So these are really linked. As we name ionic compounds, we always put the metal first, we always put the cation first, and then the anion in our formula and in our name. So for those variable charges on those transition metals and the under the staircase metals, we have to figure out what charge it must be. So in this case, we know that chloride has what charge? What does chloride do by itself? It's just a -1. So we know this is 0 overall. So the charge on copper, that could be X. And then we have the chloride is a minus equals 0. So what must be the charge on copper? 1 minus. And I'm writing it in parentheses to really show that's the charge I'm looking at. Right, X equals 1. So this must be a copper +1 together with a chloride. And remember in our naming system for the transition metals, the variable metals, that we need to use the Roman numeral. So this is going to be copper 1 chloride. So going from the formula to the name requires that you figure out what charge it's carrying and give that as a Roman numeral, but only if it needs it, not for the simple ions. Okay, so let's take a look at FeS. So figure out the one that you know, and then calculate what the one you don't know must be. We have our sulfide is 2 minus, we know just from its location on the periodic table. What must iron be to make an overall neutral compound? That must be an iron 2 sulfide, iron 2 sulfide. Okay, it works the same way with polyatomics. You have to recognize that it's a polyatomic. You have to know that these stay together. So don't ever distribute them. Always keep them together. SO4 is a 2 minus, and that is our sulfate. What must be the charge on copper? This must be a copper 2 sulfate. When we look at our naming rules, we only use Roman numerals for the metals that are variable. When we look at our periodic table, we know the simple ions, we know their charge, so you don't ever identify it. So sulfate, we have to know is 2 minus. Once we have the charge on copper, we know how many copper to sulfate. So you only write Roman numerals for these guys. Only write Roman numerals for the variable charged metals. Everything else we know the charge, so we can figure out the relationship without giving it. So phosphate, remember you have to know these charges. You can look it up. So this one has a 3 minus and there's just 1, so iron must be 3 plus. So we'll name iron 3 phosphate. The iron 3 is this one. It gives the charge. Phosphate also gives the charge. So we know the relationship because we know it has to be overall 0 charge. So let's do a few more. These ones get a little bit harder now. And I like to use my algebraic equations for these ones just to be methodical. Now, if you hate math, maybe it's not your favorite way to do it. But if you're comfortable with writing an equation, it gets you the right answer every time. or it lets you see where your mistakes are. So what do we know? Chromium or carbonate? We know carbonate has what charge? It's -2, and one way to remember is if you wrote it with colors, you can remember, oh yeah, carbonate was blue, it's a 2- charge. So that's why I like the colors. It brings in that visual learning style to help you remember. We know that it's 0 charge overall. And if we think about the chromium as our X, the charge is our X, then we know that 2x plus 3 times 2 minus has to equal 0. So this 3 right there, and this 2 is right there. I'm solving for the charge on chromium. Right? Does that make sense? This must be a chromium 3 carbonate. Okay, do you have the next one? Do the same thing for the next one. Total charge is 0. We have 4 chlorines and each one brings in a -1. If we look at tin as having that charge of X, there's just one of them. So we have a Cl- and we have an SN4+. Okay, so this is tin 4 chloride. I don't have to give the number of each thing because I know the charges. And that's true for ionic compounds. That's why we're going to name ionic compounds separately. It's a bigger process. Okay, so let's keep going, a couple more. All right, we've got 2 O2 minus and 1 lead to balance out. For the charges, it looks like X minus 4 equals 0, so X equals 4. This is a lead 4 oxide. We have 2 of those phosphates forming a neutral compound, and now we have 3, but we need to solve for the X value here. So I've changed my format a little bit. I'm showing the ions that I'm solving for. That algebraic equation is going to look like 3x minus 6 equals 0. So X equals, this is a nickel 2 phosphate. So this one, that is a nickel 2 plus. So I'm going to name it with that Roman numeral. I'm going to leave that up for a little while. We're going to do a bunch of these so we can practice and get speedy. Start with the individual ions. What do you know? You know the chloride ion. What must be the charge on the Fe? That must be a 3 plus because there are 3 chlorides. So when I name it, I'm going to name the cation and the anion. Iron 3 chloride. So again, this name refers to that ion. It gives the charge because it's a variable transition metal. Okay, so go ahead and knock through these as quick as you can. You have your polyatomic ions. If you have your periodic table, you could use that. Or if you wrote your own chart, you could refer to that. This one is mercury, and it must have a 2 plus, so this is mercury 2 chromate. So why do strontium and magnesium do not get a Roman numeral, but mercury does?
Magnesium is not in the transition element, one of the transition
And
elements.
this one is in group 2, so we know it's a 2 plus. Magnesium is also in group 2. It has to be a 2 plus. So that's why they don't need a Roman numeral. Look up your polyatomic ions and make sure you got them written down with the right charges. As you begin to finish up, be sure you check your answers. And of course, this is updating. I believe the link is active, so you can always check your answers in the OneNote notebook at Seattle Colleges.
Did you also call that last one calcium bicarbonate?
Yes. Now, like everything in chemistry, we have to go backwards and forwards. So we will also practice using the names to write the formulas. So again, write your individual ions and then think about how you name each one. Cation first, anion second. Nitride is just one nitrogen forming the negative ion. So it's in group 5, that means its simple ion is 3-. Remember, you have to do the crossover method to form a neutral compound. This is an ionic compound. It's a metal with a nonmetal. When we talk about molecules, when we're talking about nonmetals with nonmetals, then we get all that mono-di-tri business. But as long as we have a metal with a nonmetal, it's ionic, and there's no mono-di-tri. All right, so this is another good chance to get familiar with your polyatomic ion. All right, this one's tricky because zinc was an exception. It gets no Roman numeral.
So for zinc carbonate, since zinc is not either the group 1 or group 2, or I think it looks like it's a transition element. So if we don't get it in the form of compound, is there any way to find the charge?
So zinc was one of our exceptions. Go back to where we see that. Up here on page 3. It's a hard one to remember.
I think it's going to be very easy to do the math if we know the compound, like the structure of the compound. But if we don't know the compound, how are we going to do the math?
We have to either have the name or the formula. But you always have the periodic table, so you have to know these, which means you have to memorize it. For the simple ions, I drew this picture here, so let me just make it a little bit bigger. These ones are +1, these ones are +2, these ones are -1, these ones are -2, nitrogen and phosphorus. These ones, if it's the simple ion, it's a -3, but sometimes it exists as a +5. It gets a little bit trickier. But these ones here, aluminum is always a +3. Zinc and cadmium are always a +2. And silver is always a +1. So I think of it as this little corner. Those are exceptions to the variable charge transition metals. And all of the rules and then exceptions to the rules, this is what makes chemistry so maddening. It drives people crazy. There's a lot of tears in chemistry. A lot of people get very frustrated. So for those of you who might feel really frustrated or like, I just can't do this, I'll never get it, you will. It takes a lot of practice. I went the wrong direction. So these just go together. Zinc carbonate. And here's what we're going to do. Tomorrow we'll come back and I'm going to pop these up pretty quick. So try to write out your ions. Remember that the number tells me the charge. If there's no number, then you're supposed to know it from where it's located on the periodic table. Okay, I'll see you tomorrow. Thank you.